Hello, students. It has been requested that I go over some extra problems from this Unit 1 Worksheet 7 that I made quite a few years ago, back in 2015. But we are going to go over a few problems. It's been requested to do problem number 1, problem number 4, and problem number 5. Now, I got to tell you, 4 and 5 are very similar. In fact, they're basically the same problem. And they're a lot easier than number 1. I'm not sure why I did it that way, but these are a lot easier than number 1. So I think we'll go over these first, and then we'll tackle number 1 last. Problems numbers 4 and 5 are both vector problems, and I think that in a usual, normal school year, this would be a lot easier because we definitely would have been able to spend a lot more time on vectors. But I have to admit, looking at 4 and 5 now, in hindsight, they are kind of confusing. Once you get a diagram drawn, I think you'll see they're really not that bad, but they're still good practice. It's good practice for vectors, but it's also good practice for trig, which you use quite a bit in projectile motion. So problem number 4, it says relative to the ground, a car has a velocity of 16.0 meters per second directed due north. Whenever they say due north, that means straight up. And so I'm going to go ahead and add that to my diagram, because the diagram is really important for both of these problems. So I'll go ahead and draw it like that, and this is going to be 16.0 meters per second. Relative to this car, a truck has a velocity of 24.0 meters per second, directed at 52.0 degrees north of east. So what that means is, from the car's perspective, that truck is going 52 degrees, 52.0 degrees north of east, but at a velocity of 24.0 meters per second. That's from the car. We need to find out what is the magnitude of this velocity relative to the ground. And luckily, we're only finding magnitude, so we don't have to find direction, but we still have to do quite a bit. So if it's relative to the car, I am going to do what's called vector addition here. So what that means is I'm going to go ahead and draw another vector. Is it 52 degrees? I'm going to draw it something like this. And so this is going to be 24.0 meters per second. Once again, this is our truck. Down here, this is our car. Okay, and so relative to the car, the truck is traveling at that speed. So the reason I'm drawing them this way is whenever you do vector addition, okay, which is where you're adding vectors together, not just numbers, because if it were numbers, it'd be easy. It'd be 40. But when you're doing vectors, you have to take into account their direction. You always add them tip to tail. Whenever you're doing this, you always do tip, okay, to tail of whatever your next vector is going to be. So you have to draw them this way. But what we're looking for here when we do this problem is we're trying to find the resultant vector. Now, resultant vectors I always draw start to finish. Start to finish. So here's my resultant vector. Now, what this is going to give me, okay, this resultant vector, okay, is it's going to give me the truck's the truck's velocity relative to the ground. Okay, so that's what we're looking for in this problem. Truck's velocity relative to the ground. So that's what we need to find. So this resultant vector, again, you can't just add the two together. I will admit, if we did this on graph paper and maybe we did it to scale, then, and I mean like exactly to scale with your protractor, your ruler, everything, then yeah, you could just draw the line, measure the length of the line, and it'd be easy. But that's not what we're doing. So we do have to do quite a bit of trig to find our final answer. So here's the thing. The car is easy. The car is only going in one direction, the positive y direction. Okay, it's only going in the positive y direction. And so for that reason, if it's going in the positive y, we don't have to do anything else with it. The truck, well, until the end. The truck, however, has two vectors. It has an x component and it has a y component. And again, this is based on 52.0 degrees north of east. Okay, it's 52.0 degrees north of east. So whenever they say north of east, just in case you guys see it, you guys know what a compass looks like. You know, never eat soggy waffles. You know that. But the thing is, whenever they say north of east, they literally mean some angle drawn based on east, okay, measured off of east, but it is north of it, okay? So we would call this north of east. If we had something, maybe it's over here, okay? So notice I've got another vector, but I have drawn it based on west. And so in this case, we would call this south of west. And then obviously you could have all different types. Like this one here would be west of north and all this jazz. But that's really all that is, okay? So we got that drawn. What I'm going to do now is I'm going to redraw my diagram, okay, for just the truck, where I have a little more room to work. In fact, let me zoom out just a touch, and we'll come down here, and I'm going to draw it again, just to give myself a little more room to work. Okay, and what we're going to do is we're going to find the x and y components, okay? So these are the vectors that compose, you know, that 24.0 meters per second for the truck. These are the vectors that make that up. And so we're going to do that down here. Let me rewrite. We still have 24.0 meters per second. So we're still probably going to have an answer that has 3 sig figs based on that. This is an angle of 52.0 degrees, just like we had earlier. Come on, OneNote. There we go. And so now we have to find out what these pieces are going to be. Now, look, I really don't have time to teach you guys trigonometry. You can remember it by doing SOHCAHTOA, some old hippie, whatever, however you remember it. Or, you know, for now, you can look on the reference table, and there actually is a whole section over here that has to do with trig. And specifically, right angle trig is what we spend most of our time with. And as you can see, here's all the different things that you need to know with a reference triangle. So again, I'm not going to focus too much on that right now. Instead, I'm just going to tell you, we're going to use cosine to find this x component down here at the bottom. So we're going to do 24.0 degrees cosine of 52.0 degrees. Or sorry, 24.0 meters per second. I don't know why I wrote a degree. 24.0 meters per second times cosine of 52.0 degrees. Tell you what, I'll show you how we get that 1. And then the rest, you're just going to have to know how to figure out how to do on your own. So basically, if we're looking for this side, just to show you guys how I did that, let's say we're going to do this side. We are looking at the opposite side. Okay, this is the opposite. It's all based on the reference angle. So if we have 52.0 degrees, obviously the hypotenuse is the longest side. That's not confusing. Whichever side that is right next to it, okay, you can see I drew that little arrow. That's going to make this the adjacent side. And so therefore, this is going to be my opposite side. So what that means then is I'm going to want to use sine. Sine of theta is equal to opposite over hypotenuse. It's equal to opposite over hypotenuse. And so if we have the hypotenuse and we're looking for opposite, well then, just multiply hypotenuse over, right? And when we do that, we get, oh, well, the opposite side is equal to hypotenuse times sine of that theta. And again, for some of you, this may be a little basic, a little rudimentary, but for a lot of you, I bet you haven't done this in a long time. And so that's why I'm just going to write it as this. So hypotenuse is 24.0 meters per second times the sine of my angle theta in this case is 52.0 degrees. And so that's why I'm just going to write it this way. So again, that is as fast as I can possibly explain it. If you need more help with that, I guess we can talk. But honestly, you guys should kind of know that if you're in this class. Right angle trig is something you got to know. Where's the right angle? It's right there. There you go. Now I've made it a right triangle. Okay, I did this in my calculator earlier. When you guys do this, make sure your calculator is in degrees. Otherwise, you're going to have a bad time. I know a lot of math classes ask you guys to do it in radians. We really need to be in degrees. So there you go. I got my two sides. Now, the reason this is important is I'm going to make up, remember, we had to find components from this hypotenuse, but in order to find that resultant vector over there, we need to have the components that make that up. So for instance, this 14.8, that is the only x vector that we have. It's the only vector in the x direction for this problem. So 14.8 is going to go right here, okay? Then I'm also going to use that vector from before. Remember, the car is a part of this. The car's velocity, you know, that it's going at 16.0 meters per second, is something we have to consider when we're talking about the truck relative to the ground. Because remember, that speed we got for the truck is based on the car, all right? So we've got to find out from that. A simpler example of this whole problem, just so you guys understand, is the, like, baseball in a truck type deal or baseball in a bus type thing. So if you've got a bus going down the road at 20 meters per second and a person sitting in the back throws the ball forward at 20 meters per second, and think about it this way. Let me say it again. Bus going at 20 meters per second, ball gets thrown towards the front of the bus at 20 meters per second. From the perspective of someone in the bus, they would say, oh yeah, I threw that ball at 20 meters per second. But for a person watching the bus go by, they're going to say, man, that ball was thrown at 40 meters per second. because relative to them, they see it going at 40. So we have to consider both. We have to consider both, all right? So right here, let's make that happen. 16.0 meters per second is going to go right here. And then that 18.9 that we found from just the truck is going to go right here. So we get 18.9 meters per second. It's going to go right there. All right. Now, at this point, because 16 and 18.9 are both pointing in the positive y direction, by the way, not like you have to have it, but if you want to have a little reference over here, you can. Okay, there you go. All right, but anyway, it's in the positive y direction. Because they're both pointing in the same direction, we just add them together. So we add these together, we end up getting 34.9. And that is definitely kosher. As you guys know, significant figures, when you add things, are based on the least number of decimal places. Both of these are to the 10th place, so 34.9 is just fine. So here's the deal. At this point, we have an x side to this triangle. We have a y side to this triangle. And so for that reason, now we can just use Pythagorean theorem. So let me go over here. I'm just going to write Pythagorean. There we go. Pythag. That's all we're doing. Let me move something out of my way. There we go. And so if we're going to do the Pythagorean theorem, we can definitely do that. You guys know Pythagorean theorem, okay? It's one of those things that you know. Mitochondria's powerhouse of the cell, and a squared plus b squared equals c squared. So if we are trying to find c squared, okay, that's why you can just do the square root of this, right? And that gives you the answer. So going kind of fast here, but basically we have our two sides from before. Let me back up just a little bit and recenter. We know that 14.8 is going to be one side, so that's 14.8 meters per second squared plus, now we have my other side, all right, which is 16.0 plus 18.9, which we got is 34.9. That's the y component of this, so that's going to go here. And we're going to square root all this to find our hypotenuse, which I made a variable name. You can call it VTG, which means velocity of truck relative to the ground, okay? So what we end up doing, you do this in your calculator. Be careful with your order of operations. I ended up getting 37.9 meters per second, and that is a perfectly fine answer, okay? Let's let OneNote catch up to me. 37.9 meters per second. This is fine. 3 sig figs. That works. And also, no direction was required. If you look back at the problem said magnitude. Okay, what is its magnitude? So we don't need direction. We're good to go. Let's quickly look at number 5. Ferry boat is traveling in a direction that is 38.0 degrees north of east. All right, so once again, let's go ahead and get started by drawing a picture here. Okay, let's go ahead and draw a picture. So this is 5.50 meters per second, okay, at an angle of 38.0 degrees. Obviously, I'm not drawing this to scale. That is definitely not what 38 degrees looks like, but it'll work. And this is all relative to just some x-axis, which I guess is east, because this is based on east. At a speed of 5.50 meters per second. Yeah, we did that. A passenger is walking with a velocity of 2.50 meters per second due east. So let's go ahead and draw another vector for the passenger. And remember, I'm drawing these tip to tail. So that's why I'm drawing it up there instead of like down here. Okay, some students are going to think, oh, well, wouldn't you just draw it down here? No, 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 no. Tip to tail, guys. Tip to tail. So we're going to put it right there. And so that's 2.50 meters per second. The reason it's pointing to the right is because it's going due east. Okay, so we're good. What is the velocity of the passenger with respect to the water? Guys, it's the same problem as before. Okay, we are going to try and find the resultant vector here. Okay, so I'm going to just write right here, we need the resultant vector because we have the passenger relative to the boat and we have the boat relative to the water. But if we find the whole resultant vector, that'll give us the speed of just the passenger relative to the water. Okay, guys, same thing as before. 2.50, there's not a lot to do with that right now because that's only pointing in one direction. But because 5.50 is pointing in both the x and the y direction, okay, because it's based on an angle of 38.0 degrees, then I can go in and find the sides. All right, so we're just going to use trig again. This is still a right triangle. You'll see over and over again that we just do right angle trigonometry in this class. All right, so we get this. And again, I'm not going to explain where these are coming from right now. You guys should know how to use sine, cosine, and tangent in this way. But we have 5.50 meters per second times the cosine of 38.0 degrees down here. And on this y component, we're going to have 5.50 meters per second, sorry for my handwriting, times the sine of 38.0 degrees. And once again, I went ahead and calculated this ahead of time. We get 4.33 meters per second for the x side of this. We get 3.39 meters per second for the y side of this. And now we're going to build our resultant vector. So the 4.33, it is in the positive x. So I'm going to draw it to the right. Okay, so here's 4.33 meters per second, goes right there. And I can go ahead and bring down this vector now of 2.50 meters per second and put it in the right place. The reason it is okay to just add 4.33 and 2.5 together is because they're pointing in the same direction, okay, which is the positive x, and because of that, we can just add them. This is okay to just add, nothing fancy. So when we do that, I get an x component of 6.83 meters per second, okay, meters per second. There we go. As for the y component, we found that too, okay? So it comes from that sine of 38 degrees times 5.50 meters per second. And we got 3.39 meters per second. So there's our y component. And now we're in business. So same as before, all right? Same as before. It's going to be really useful to just find this using Pythagorean theorem, okay? So we want to find this using Pythagorean theorem to get the magnitude. Okay, so this is where we get the magnitude from. And by the way, if you look in the problem, we have to have magnitude and direction. So we got to do just one extra step for this. Okay, let's let OneNote catch up really quick. There we go. So we're just going to use Pythagorean theorem. Same as before, guys. I'm not going to write it out. You guys should get this. We're going to do 6.83 meters per second squared plus 3.39 meters per second squared. And by square rooting this, we can find, let's call it velocity of passenger relative to water, or VPW. There you go, because that's what we're looking for. So ... you put it in your calculator. Be very careful with your order of operations, like I told you. And we get 7.63 meters per second, okay, at what? We don't know the direction. Okay, we don't know the direction. So the extra step that we have to do here is we have to find out what that direction is. Magnitude is the same as before. But in order to get the direction, I'm actually going to rewrite the whole resultant vector triangle over here. Try and get a little bit closer to what it actually is. So we said that the x component was 6.83 meters per second. Same as before, same as before. We said the y component of this resultant vector was 3.39 meters per second. So we'll put that right here. VPW, we don't really care because we don't need it. But we're looking for theta, okay? We're looking for theta. And using kind of what I taught you guys from before, okay, look on this side. This is the opposite because it is across from an angle theta. This other one is the adjacent because it is next to the angle theta. So we got opposite and adjacent, which fans of right angle trig should know means we're going to use tangent. If you don't believe me, here's the rule for tangent. So tan of theta is equal to opposite over adjacent. And the inverse tangent, so tan -1 of opposite over adjacent, gives you theta. So both of these are really useful, but obviously we're looking for theta. So we're going to use the inverse. Come on, OneNote. There we go. So inverse tangent of opposite over adjacent gives you theta. So we want to use that. So I'll just plug in some information. Inverse tan of opposite, 3.39 meters per second over adjacent, 6.83 meters per second is going to give me theta. ... math happens. I put it in my calculator. I got 26.4 degrees. And that is our direction, okay? Now, just to keep the same kind of naming convention that they were using, let's think about this relative to a compass, okay? So here we go. There's north, south, east, west. And so really my angle is north of east. It's really north of east. All right, so let me clean this up. And there you have it. Magnitude, direction, we are good to go. All right. Okay, guys, now for the really fun one. So both of these were kind of the same. It's just vectors, resultant vectors and component vectors. And just to remind you guys again, resultant vector is the whole thing. Component vectors are what you use when you have something that's at an angle and you need to find the x and the y components. That's why that's important. Let's look at number one. This is the one that's super fun. You guys are going to love it. Okay, it's complicated. A projectile is launched from ground level at an angle of 12.0 degrees above the horizontal. It returns to ground level. Okay, to what value should the launch angle be adjusted without changing the launch speed so that the range doubles? Okay, guys, this is a hard problem. This is pretty standard for AP Physics, though. It's algebra based. So the first part is still determining basically like, okay, what are the physical things that I know about this problem? So you're still making your list, you're still doing all that stuff, and then you do have quite a bit of algebra, which I'll help you with in a second. But I always find that the hardest part of these types of problems is trying to determine, okay, what do I actually know? What is true? What can I set equal to one another to try and simplify this a little bit? And by the way, if you want to have a little coordinate plane, it's not super useful. But if you wanted to have a little coordinate plane and say, yeah, positive y is up, positive x is to the right, I mean, it's kind of useful. Not so much for this problem, but for other things. Okay, so I'm going to make a list for y, and I'm also going to make a list for x of things that I know to be true. The first thing I want to write down is this. In the y direction, a is equal to g. And the reason I'm writing that as lowercase g is because if we are dealing with an object that has been launched and it is on Earth, it is going to be equal to acceleration due to gravity. So I'm just going to go ahead and rewrite it as g. I'm not going to make it a in the y direction and do a subscript y or do any of that stuff. I'm just going to make it lowercase g for acceleration due to gravity. We don't know what the time is, but that's okay. I'll explain in a minute. And this is what we do know, okay? We can think about this in terms of final y velocity and also in terms of initial y velocity. We need to consider both of those because we do know a little bit. For instance, if it is launched from ground level with a certain, y velocity, when it comes back down to ground level, it's going to be the negative of that. Maybe you guys have heard the phrase, what goes up must come down. Okay, if you haven't, now you have. But think about this. If I were throwing something directly up, and I throw it up at 5 meters per second, it's going to come back down with a velocity of negative 5 meters per second in the absence of frictional effect. So no air resistance. If I throw it up at 5, it comes back down with negative 5. So here's what I'm going to write down then. My final velocity is going to be equal to the negative initial velocity. My final velocity is going to be equal to the negative of the initial. And I'll talk more about that in a second. So what this means then is this is the equation I'm probably going to want to use. So velocity of the y is going to be equal to v naught y plus at. This is just a good equation to use. We don't want to mess with displacement in the y direction. We don't care how high it goes. So we're not going to play with that. This is the equation that we want. Now in terms of x, you guys should know by now that there is no acceleration in the x direction. And so for that reason, this is the stuff that we know. We know v in the x is equal to something. More on that in a moment. Delta x is I'm just going to rewrite it as r, just for the range. Okay, this problem talks a lot about range, so we're just going to call it r. And we don't know t. But the only equation that we can use in the x direction, because there's no acceleration, is vx equals delta x over t. Okay? Vx equals delta x over t. That's the only equation we can use because it does not have acceleration in it. It's not accelerating in the x direction. There's no gravity acting in the x direction. And one thing that I think might help you guys is I am going to make another triangle because this problem is talking about what is going, what should you change the launch angle to without changing the launch speed. So I'm just going to make the launch speed an ambiguous v. So if we have v in the x, that's the x component. If we have v in the y, that's the y component. But v is just the launch speed at 12.0 degrees. Sorry, dog is getting excited down there. At 12.0 degrees above the horizontal. So here's what I'm going to do. Using the same kind of stuff I've been telling you guys, we are going to find the component vectors. We just practiced trig a lot. And so what that means then is my v in the x is going to be down here. My v in the y is going to be up here. But we can solve for what this stuff is based on v and theta. So in this case, vy, that's just going to be v sine theta. And if you don't believe me, you can check your trig. But it's going to be v times the sine of theta for this component. And so that means this one down here is going to be v cosine of theta. So see, instead of having multiple different variables, whenever possible, try and simplify it down. So instead of having v in the x, or v initial in the y, or v final in the y, I've now got it down to just v, the launch speed, and theta, the launch angle. And that makes it a lot easier. So I'm going to fill this information in on my list just for consistency's sake. So v in the x is now going to be v cosine theta. V in the y. Sophie! No. Sorry, she's got a very loud bone. I should probably have taken that away. Vy is going to be v sine theta. Okay, and by the way, this would be v naught y is what we solved for on that triangle because that's the launch velocity. And then obviously when it's on the way back down again, right, it goes up and it comes back down. When it's on the way back down again, this is just going to be negative v naught y. And so that's why I'm going to go in and say, oh, well, this is equal to negative v sine theta. Excuse me one moment. Everybody is trying to call me. This is actually the second time I've tried to record, and I've had family members call me both times. And so this is the second, nope, this is the third attempt. But anyway, here we go. So now that we've got our list, this is actually the hard stuff out of the way, and the rest of this is algebra. That's all the physics. The rest of this is algebra. So let me show you what I mean. So using my two equations, I now want to start to simplify this a bit. Okay? I'm now going to have to simplify this a little bit. And I got a text. All right. Sorry, guys. Now what we need to do is rewrite these equations again, and I'm going to show you what we're going to solve for. Because remember, whenever you have multiple equations, okay, whenever you have multiple equations, you really want to try and get it down to just one equation with, again, as few variables as possible. So here's that equation we wrote earlier. Here's the one that we wrote earlier for the x. Okay. Now remember, this problem is looking for the range. Okay, this problem is looking for the range. What is the range of this object? And so because of that, we're going to end up rewriting that equation in terms of r. So this is going to be vx times t. So r equals vx times t. And so now we have the range. And so remember, guys, from way back at the beginning of the problem, we did not know what the time was. All right, we don't know time in the y, we don't know time in the x, but here's the thing. Time has no direction. So whatever time it is, it's going to be the same for both. So what that means then is if I can solve this y equation in terms of t, I can plug that in for time in my x equation. So here's what I'm going to do. I'm going to divide over, or no, I'm going to subtract over v naught y first. And by the way, I've already plugged in negative v naught y for y because like we said, vy, the final velocity, is just the negative of the initial velocity. So I'm going to minus that over. And when I do, I end up getting this. Negative 2 v naught y is equal to g times t. Okay? Negative 2 v naught y is equal to g times t. Let's go ahead and divide over g. And when we do that, the g goes away. Isn't that great? And so we end up getting t, let me rewrite this and clean it up, is equal to negative 2 v naught y over g. All right, so t equals that, negative 2 v naught y over g. And so now we can plug that in for time over here. Okay, so now what we get is r equals v in the x. And I know I'm gonna plug in what we know here in a second. But v in the x times -2 v naught y over g. Okay, just like so. And now I'm going to start to plug things in. So from before, I told you guys we know all of this based on this triangle that we made. So I'm going to rewrite it in terms of these variables that we got from the triangle, just so we can get rid of some of these. Okay, so instead of having vx and v naught y, I can get it in terms of theta and velocity, which is really what we're looking for. Okay, so here we go. Let me rewrite all this. We get r equals v cosine theta times -2 times v sine theta, okay, all over g. So see, all I did is now I'm using the stuff that I solved for based on the triangle earlier. All right, so I plugged all this in just like so. So now what I'm going to do is I'm going to rewrite this a little bit. I'm going to try and simplify it because if we have v times v on this right side, because we do, it's right here and it's right here, that's just going to end up becoming v squared. And so I'm going to simplify this a little bit just intentionally because I know what's coming next. So this is going to be -2v squared, okay? Or do I want to write that different? No, that's fine. Sine of theta times cosine of theta. Okay. Yeah, that's fine. I'll leave it that way. And this is all over g, same as before. So again, it's the same stuff. I've just rewritten it. And I got to tell you, this is where the algebra gets just so fun because we are actually going to do a trig identity. If you don't know what a trig identity is, it's like where sine divided by cosine equals tangent. So like a sample trig identity that I've used a lot is sine of theta over cosine of theta is equal to tangent of theta. So like that's a trig identity you use a lot. That is not one that we're going to use here. There actually is another trig identity that looks like this. Okay, so here we go. Trig identity. I'll show you where I'm getting this here in a second. It's going to be 2 sine theta times cosine of theta is equal to sine of 2 theta. Sine of 2 theta. Here we go. Let it catch up, and then I'll show you what I mean. So 2 sine theta times cosine of theta equals sine 2 theta. And that is really what we have. If you look over there in the numerator, that's really what we have. So I can now rewrite this. Now look, let me show you guys this. I've actually put it in OneNote. So look, we're in Narren folder, general. And yeah, we got all this trig stuff. That's great and all, but I actually found this website not too long ago, and this has all the important trig identities on here. So like here, that right there, okay, tangent of theta is equal to sine over cosine. It also tells you what cotangent, secant, and cosecant are equal to. So that's kind of helpful. That one right there I've used before. Sine squared theta plus cosine squared theta equals 1. But if we look down here, that's the one that I'm applying right now. Okay, so that's the one that we're applying right now. So that's all. As you can tell, I don't have them memorized, but it is something that we need to solve this problem. So let me rewrite and you can see where we're at. Okay, so rewriting with that trig identity, trying to keep track of my notes so I don't make a mistake. We're going to get v squared times sine of 2 theta, all divided by g. Okay, isn't that nice? See, that's so much nicer from before. So at this point, let me explain where we're at. Okay, we want a ratio, really. R2 over R1 to be equal to 2. We want R2 over R1 equal to 2. Because remember, we want to double the range, okay? And we want to find out what do we need to do to theta to make that happen. So if we're doubling the range, that means R1, okay, is going to be the range where theta 1 is equal to 12.0 degrees. So that's the one that we're dealing with in this problem that they gave us. Okay, so if R1 is the range, come on, where theta is equal to 12.0, we're looking for, what is R2 going to be? Or what is theta going to be for R2? So let me try and put that into a simpler sentence now that my dog's not running around and distracting me all crazy. So the thing is, if we're doubling the range, that means R2 over R1 is going to be equal to 2. It's twice as much. And so that's why we can do this. So I think you guys probably know what's coming. Now we can do this. All right, and it's going to get super fancy. R2, okay, so this would be our doubled range. Is now going to be equal to V2 times sine 2 theta 2, I'll explain that in a second, all over G. And we're going to divide all of this by R1, which is going to be V squared times sine of 2 theta 1 all over G, like so. Okay? Now look, theta 1, as I just said, is 12.0 degrees. Theta 2, we don't know what it is, but we're trying to find what theta 2 is because we want to determine, okay, well, what is the angle going to be in order to double the range? So that's really what we're doing here. Now, the fact that we're dividing means that now we can do a whole lot of canceling. So see, if I've got v squared on top, I can get rid of v squared on bottom. If I've got g on top, I can get rid of g on the bottom. And so now we can rewrite this. So basically what we're saying is this, okay? R2 divided by R1 is equal to 2, which is equal to, I'm just going to rewrite what I didn't cancel. Sine of 2 theta 2 over sine of 2 theta 1. So see, now we've gotten rid of R2 and R1. They're out of the picture. Okay, in fact, we're gonna ignore it now because basically we've said that's equal to 2. That's a number, and that's really important. And so we've applied that ratio, which again is just based on physics knowledge of understanding what this problem actually means is going on. We have now simplified and made things a lot nicer. And again, I always tell you guys, put it off as long as you can stand it. But now we have to plug some numbers in. Okay, so now we have to plug some numbers in. And remember from before, theta 1 is 12.0 degrees. And so I'm going to plug that in. She's running around again. Okay, so now I can plug in some numbers. Let me rewrite it just to make it all purty. 2 is equal to sine of 2 theta 2 over sine of 2 times 12.0 degrees is really what we're dealing with. We do some math. I end up getting, for the denominator down here, I got 0.407. And so because I'm dividing by 0.407, remember, we're trying to get theta 2 by itself. So if I'm dividing by 0.407, multiplying by 0.407 on both sides will allow me to get rid of that. Okay, and so we're going to do 0.407 times 2 over on the left. And now let's get this cleaned up a little bit. I always think it's a good idea to show your work like this because first of all, it's what I'm looking for. And second of all, it keeps you from making mistakes. And the AP graders, they're going to want to see your method. So every now and then I like to clean it up just so I know what I've still got. Otherwise, you just get super confused. So this is what we're dealing with. 0.813 is equal to sine of 2 theta 2. All right. Now, let's go ahead and wrap this up. I've explained quite a bit, but you end up getting theta 2 equals the inverse sine of 0.813, and this is all going to be divided by 2.00 if you care. It actually doesn't matter. That's infinitely significant because that was just a math 2. That wasn't a physics 2. That was a math 2. It wasn't based on a measurement is what I mean. So what we end up getting is theta 2 equals 27.2 degrees. And that's our answer. So as you guys can see from all of this junk, okay, is again, the physics is half of it. Can you make a list and identify what everything means? Can you get the, from the physical description, can you get the mathematical representation? And then the rest of it is just this algebra. So there you have it. Hope this was helpful for you guys. I'm sorry for the distractions of people calling me. I'm now going to call one of my family members and see what's going on. And I hope you guys enjoy this and get something out of it. Thank you very much.